To propagate from system to system across the internet, the Morris worm exploited technical vulnerabilities in several Unix programs. In this video, I'll talk about how the Morris worm spread by exploiting a vulnerability in the fingerd program in Unix. And my goal here is to go into a bit of depth regarding the mechanics of how this vulnerability was exploited, but I'll still try to provide enough of a high-level explanation to make the content at least partially accessible to a broader audience. The fingerd or Daemon program in Unix is a program that runs on a server. It typically interacts with a client program known as finger, and what the finger utility allows one to do is determine the status of a given user on a system. So, for example, if my username were Zulfikar on a given host, and let's say we'll call the host example, then one could actually type the command finger Zulfikar example on a Unix system, and the finger client would communicate with the finger daemon running on the host called example, and this example host would reply back with information regarding me on that system, assuming that I had a legitimate username on that system. And that information might include, for example, whether or not I'm logged in to the system when I last logged in, maybe information about my physical coordinates or things of that nature. Now, typically, the fingerd program on a server expects a relatively short username, something that's under 512 bytes. And that's fairly reasonable, because users generally don't have unusually long usernames. So the fingerd program allocates a data structure on the system known as a buffer, and that buffer can hold up to 512 bytes. Now, underneath the hood, the fingerd program uses a well-known subroutine in the C programming language called getS, which, as the name might imply, is used to read in or to get a string. And in the case of the fingerd program, this string corresponds to the user and host name that is supplied by finger. Now, getS will basically read in the username and store that username in the buffer that was allocated to store that username. However, it turns out that the getS subroutine in C does not actually check if the username that was supplied is within the right size bounds. And because getS fails to perform this check, if you happen to provide a string, or if an attacker for that matter provides a string that is longer than 512 bytes in length, then that string will overwrite past the length of the buffer and will cause data to be written to other system data structures. And in particular, information can be then written to a system data structure known as the system stack. Now, if this step is carried out carefully and meticulously enough, an attacker can actually alter the flow of the fingerd program and get it to perform essentially in an arbitrary fashion that is under the whim of the attacker. And this particular class of vulnerability, where the buffer is overwritten, and in doing so the attacker gains essentially arbitrary access to run code of their choice on the system, that class of vulnerability occurs in many places. It's a very common type of vulnerability, and among people in computer security, that vulnerability is often referred to as a buffer overflow vulnerability. So if you've heard this term buffer overflow, it refers to this type of vulnerability where a system buffer is overwritten, and if done carefully enough, the attacker can then control execution and run arbitrary code on that system. It is really one of the most common software vulnerabilities out there. For the Morris worm in particular, the finger request that was made to the finger daemon on the server that was being targeted was actually accompanied with a 536 byte, very carefully constructed artificial username. So that size exceeds the 512 bytes that were allowed. Now, the first 512 bytes of this artificial username contained no ops, meaning they don't do anything on the system. The remaining 24 bytes comprise two pieces of information. The first piece is a special return address, and this return address tells the computer specifically where it needs to look next to determine what additional instructions it has to execute. The second piece of information that is specified among these remaining 24 bytes indicates exactly what to execute. In this case, it starts what's known as a standard command shell or a command interpreter, known in Unix as sh. And what happens is the return address is set up so that it tells the computer to start executing code at the location of the computer's memory that contains this instruction to execute the shell program. And in particular, when the finger daemon finishes running, in general, control was supposed to have been passed back to whatever it was before, but because that address was overwritten with this artificially long finger command, control actually ends up getting passed over to the place where the newly written address points, which, as I just mentioned, now contains a command to execute the Unix command shell. And the shell is basically set up to send and receive commands from what's known as a socket. You can think of a socket as basically representing just one side of the communication between two entities on a network who are communicating. For example, that network could be the internet. On one end of this socket, in the case of the Morris worm, would be the Unix shell program running on the server that was just compromised. And on the other end of the socket is the modified finger program that was used in the Morris worm. So the worm can now send commands to the server that it is compromising, and the server, because it is running a shell or sh at the other end of the socket, will dutifully run those commands. And so in particular, the worm will actually send commands via the socket, and what it sends is a command, first of all, to copy itself over to the compromised system. So it sends a copy of itself to the compromised system, and then it issues a command to have that copy executed on the remote system. And so in this manner, the Morris worm could propagate over the network via the finger daemon. And this exploitation of the finger daemon was just one of several different mechanisms that was used by the Morris worm to help it propagate. I thought it was a very clever exploitation of a technical vulnerability, and it is considered among many to be one of the more noteworthy features of the Morris worm.